All right, part 3 of our glycolysis set of lectures. Here we come. Our goals in this set, or in this lecture, is now to really look at the fate of pyruvate in the case of anaerobic metabolism, and to look at the different entry points for carbs into that glycolysis pathway. So we're really kind of looking at the beginning and the end of the cycle. Now, if we look at our metabolism chart, remember here's a blow up piece, and our glycolysis starts with glucose and ends at pyruvate. And if you look at this, there are all sorts of arrows going to and from pyruvate. There are lots of different things that can happen to form or to react that pyruvate. So it's a really important metabolite, a really important molecule that is made as part of this metabolism process. All right, this is our 10 steps of glycolysis. So we've now had 3 separate summary slides. My favorite is the one in the first video. But here you have a unannotated set of the reactions. All right, you should take the time to go through each of these steps. Go through it slowly and think about each substrate, right? What are we starting with? What's changing as we go to the next step? What enzyme is doing that? Do you need to memorize every enzyme name? No, but you should know things like hexokinase. Oh, well, that should be a kinase. It should be something that's going to phosphorylate that 6-member sugar ring. Okay, so you should be able to make those linkages. So you should have a feel for the function of each of those enzymes as we go through. All right, so this is really just there for your review. I stuck this question in here just to highlight kind of what I would expect you to be able to do. So here's the question. Which enzyme in the glycolysis pathway catalyzes the oxidative reduction, or I'm sorry, the oxidative addition of phosphate to the substrate? And when I think about, first of all, we're adding a phosphate, that's going to kind of highlight some things. But the other key word here would be that oxidative. We're talking about a redox reaction. And if you've looked through your reactions and you've reviewed the ones we talked about, I highlighted in the last video this dehydrogenase, this important reaction, redox reaction step. And I said, hey, you should think about redox reaction when you see dehydrogenase. And it turns out this is actually the answer. If you go back and review each step, you'll see this was the redox reaction where we added that phosphate. Okay, but now moving on to our material for this particular lecture. All right, we're going to talk about the different fates of pyruvate. What can happen to this? So in the vast majority of organisms, macroorganisms, microorganisms, this pyruvate will move on along to form the acetyl-CoA, and then the acetyl-CoA will go through the citric acid cycle, electron transport chain. Most of the pyruvate, this is where this will happen. Okay? And this is an aerobic process. On the left, we have our anaerobic options, and there's 2 different options. All right, the one on the far left, this happens in yeast, certain bacteria. And we'll look at this reaction, but what we see is pyruvate had 3 carbons, and it gives off one of those carbons as a part of carbon dioxide and leaves us with acetaldehyde. And then we see so think about this step, NADH going to NAD+. You gotta think, is that being reduced or oxidized? That is being oxidized. So the other reaction must be reduced, and we get ethanol. So one end product of this anaerobic process would be ethanol for yeast and certain bacteria. In animals, instead, when we have that anaerobic process, we're going to get lactate. Okay, we still have a redox reaction, but now we're going to get lactate. Let's look at how these happen and kind of why we need these anaerobic processes. So fermentation's means of oxidizing that NADH. So let's take a look at that alcoholic fermentation. So we have pyruvate as our starting material right here. Notice the name, pyruvate decarboxylase. So decarboxylase, so it's taking this CO2 off, and we end up with our now 2-carbon molecule. And if I look, I can see that as this molecule goes here, okay, it's being reduced, and I have fewer bonds to that oxygen. That is paired with the NADH being oxidized. An important key here is that we get this NAD plus back, and that NAD plus is a key piece for our glycolysis. It's needed for our glycolysis steps. So let's take a look at that. So here were our glycolysis steps. So over here, we had a chunk of our glycolysis reactions. Okay, and now we're saying, all right, in anaerobic situation here, our pyruvate could be changed to ethanol, reacted to form ethanol. And look what happens. Back for this early reaction, okay, we had this co-substrate of NAD plus, and it was reduced to form the NADH. And now, if we get over here, we can now oxidize that, and we get that NAD plus back. So it can feed back into the cycle and allow that glycolysis cycle to go on longer, go on more, because we have that NAD plus. All right, let's look at lactic acid fermentation. So again, a key piece of that. So notice what we have. We have our starting point, glucose. We get 3 steps. We get to this key point where it breaks into 2 smaller molecules. So we have step 1, step 2, step 3. Oh, we got step 4 where we get 2 different molecules, but step 5 brings them both back where we have this gap molecule. And now we get down to pyruvate. And it can, if in aerobic conditions, it can go on and become the acetyl-CoA, etc. But in anaerobic conditions, we again see this process, all right, where we can oxidize our NADH to get that NAD plus back. And that can feed back in up here in our glycolysis cycle and provide that needed co-substrate. All right, so you're seeing that here as we look at that reaction. So we have the lactate dehydrogenase. So dehydrogenase should trigger that. Ooh, this is probably a redox reaction. Okay, and we can see that the pyruvate can form lactate, and that when we react glucose, we can get 2 lactates if it follows through this this general area. All right, so a question. Lactic acid fermentation and alcoholic fermentation are redox reactions. Identify the ultimate electron donor and electron acceptor. And normally we're just going to look at one reaction and talk about what is being oxidized and what is being reduced. But when we think about the donors and acceptors, what is ultimately giving electrons, what is ultimately taking electrons, right? We have, if you go back and look in your glycolysis, and you'll find we have that glyceraldehyde 3-phosphate molecule. That was in that first reaction with our dehydrogenase, and that donated electrons to our NAD+. Okay, so this is like the original donor of electrons. And then they get carried through various reactions. Okay, the ultimate acceptor of electrons, if we look at it, in that lactic acid reaction, is the pyruvate. It's accepting the electrons at the end of that cycle. Okay, or for the ethanol, there was actually a middle step, so it's actually acetaldehyde. So depending on which of those steps it was. I don't want you to stress about that too much, but it's an interesting kind of thought process to go back and look at those reactions and follow the electrons. All right, let's talk a little bit about hexoses, so these 6 carbon sugars other than glucose. And as we talk about these, we could think about fructose from table sugar or the high fructose corn syrup. We can talk about galactose from milk sugar. And these all get converted into this glycolysis, some of these glycolysis intermediates. So for example, galactose has a multi-step enzymatic process that ends up dropping it into the cycle right here, okay, with that phosphorylated glucose molecule after that first step. So galactose skips this first step right here and drops in right there. Fructose can actually come in several spots. So one of them, if you have fructose in tissue like fat cells, it can get phosphorylated and enter right here when we first made that phosphorylated fructose ring. Okay? But most of the fructose from your diet is going to enter through the liver. And when that happens, there'll be several steps, but it gets converted into one of those 2-3 carbon molecules we have right at the end of the energy consuming first 5 reactions from glycolysis. So fructose that you have in your diet, so from like high fructose corn syrup and things like that, gets dropped in right at the end of that energy investment phase of the glycolysis pathway. And that is a bit problematic. Because if you remember, we talked about the main regulatory step that tells glycolysis if it should go forward or not. We said that that was moderated by our PFK enzyme, and that was based on the energy needs of the cell. It will either turn glycolysis on or off, and it's right in here. And the key thing is that is before fructose is dropping its molecules into the cycle. And so this is really a problem because fructose enters the cycle past the regulatory point. So as it enters the cycle, it'll turn it on and drive it forward even when we don't need it. So we can end up with too much pyruvate, too much acetyl-CoA, and then if it's not needed for energy, it won't go into the citric acid cycle, so then it gets transformed into fatty acids, triglycerides. So this is why when you hear about excessive fructose consumption, or sometimes you'll see sodas that say made with, pure sugar, not high fructose corn syrup. And this is the problem that you can run into with this, is that excess fructose consumption has been linked to obesity, fatty liver, development of type 2 diabetes, in large part because it bypasses that regulatory enzyme of glycolysis. All right, that is the end of our third out of just 4 glycolysis videos. So we have one more lecture on glycolysis to go, and then we will move on. But thank you for paying attention at this one.